Hi, welcome to Calculus. Today we are looking at moments and centers of mass. So this is going to be kind of fun. We're going to do a little bit of physics. Basically what this comes down to is we're looking at mass at a distance. So the most obvious example to me anyway, or maybe the easiest one to figure out, is your basic teeter-totter. You put a person on each side. If they weigh the same, it balances, and if they don't weigh the same, well, it doesn't. And hopefully nothing really horrible happens, like somebody really big gets on the one side and with a small child on the other, and whop. Anyway, so we're going to start here by looking at along a line. So I have a fulcrum here drawn in. Think of that as the middle of my teeter-totter. And along my line, I have three masses, M1, M2, and M3, that are at various distances from that fulcrum. So the torque for any one of those masses is equal to its mass times the gravitational constant times how far away it is from the fulcrum. And in this case, distances on the left of this would be positive and distances on the right would be negative because a positive torque goes counterclockwise. So the system torque, if you take this whole system and add up the torque that's present, you just add up all the m sub k's times gravitational constant times the x sub k's. Long story short, you can factor out the gravitational constant and just add up each mass times its distance. Well, mass times distance is what we're going to call a moment. So let's keep that one right in the front of our heads. A moment is a mass at a distance, okay, or mass times distance, really. And so the system moment, m sub 0, is the sum of those mk's times the x sub k's. All right, so continuing on then, if we know what the moment is, we're going to be able to find out where the special location of the balance would be. So in this little tiny drawing I have here, where would we have to put the fulcrum to make the whole system just stay balanced? Well, so the special location for balance is called the center of mass, and it works out to be the system moment about the origin divided by the system mass. So you just add up all the mk's times xk's, and then you divide that by just the full mass. You add up all those masses. And so that's along the line. So now we're going to take it into two dimensions, and we're going to do some fun stuff. So hang on just a second while I change the board. Okay, so continuing on, let's take it into two dimensions now. Let's look at masses in a plane. So I've drawn a set of axes, x and y, and I put one mass into my system. Keep in mind, we could have lots and lots of masses. My picture just has one. So each mass in the system, we'll call it m sub k, because you could have m1, m2, however many, but each mass has an x and a y coordinate where it exists. And so here's what we really want to think about with this mass. The mass for the system is still adding up all of those masses. That hasn't changed. But now for these moments, we're going to have two of them because we have two different directions that we're really looking at here, the x direction and the y direction. So the moment about the x-axis, this is based on how far away the mass is from the x-axis. So it's a little bit weird maybe to get used to, but the moment about the x-axis is the sum of the masses times their y distances, those y coordinates. Again, because it's how far away are we from the x-axis, we're looking at, rotating back and forth, that teeter-totter again, with the x-axis as our fulcrum. And same thing with the moment about the y-axis. M sub y is equal to the sum of the masses times their distances on the x, times their x values. Again, distances from the y-axis. All of which then can get us centers of mass. So if you have masses in a plane, the centers of mass have ordered pairs for their coordinates, x bar and y bar, where x bar is the moment about the y-axis, because that's going to be an x coordinate, right? The moment about the y divided by the system mass. And y bar will be the moment about the x-axis divided by the system mass. So again, you're adding up all those individual masses for these m's. That's what we had over there. So again, it's a little bit weird to hear some of this notation, right? We have the moment about the y-axis, but we're using x coordinates. But that's because x coordinates are how far away from the y-axis you actually are, and vice versa with the x-axis and the y coordinates. All right, let's continue. All right, so the last thing we need before we jump into some examples is we need to take a look at thin, flat plates that are going to have even thickness and density for our purposes. You can make your life a little bit more miserable if you give up those two things. We will not be in our class. So we have a plate here, and what we want to do is we want to consider it as a bunch of little rectangles. So we've seen rectangles before, we did them when we started integrating, and we're going to do something pretty similar. We're going to make a typical rectangle in the middle of our plate. So you can see I drew a rectangle here, and each rectangle will have its own center of mass, and we're calling that x tilde y tilde. And so we have an x and y coordinate for the typical center of mass for each rectangle. Okay, and we'll look at finding that center of mass here in just a little bit. So what we're going to do then is we can find the mass of the whole plate by taking the integral of dm. Now what's dm? Well, dm is basically the density times the area. One of those probably is a function. It's going to have an x in it or a y. So the mass is just the integral of the density times the area. And by the way, we could draw strips that were horizontal, and then we'd be looking at something just a little bit different. All right, so anyway, mass is integral of the density times area. The moment about the x-axis, so again, that's going to be y coordinates, because we're looking how far away are we from the x-axis. The moment about the x-axis is the integral of the typical y coordinate times, again, the dm, that density times area. For the moment about the y-axis, we have the integral of the typical x-coordinate for the center of mass for each strip times dm. And so for the whole thing, its center of mass will be at x bar y bar, where x bar, again, just like before, is m sub y over m, and y bar is m sub x over y. All right, time to do a couple of examples. All right, so let's find a center of mass and moments and all that kind of good stuff. So here's my region. I have this region, it's a triangular region that goes over 2 on the x-axis and up to 4 on the y-axis. Now, it's worth pointing out this diagonal here is the line y equals 2x. We wouldn't necessarily have to be given that. I definitely expect that you could find the equation for a line. That should be relatively straightforward for you. In this case, it goes through the origin, so its y-intercept is 0, and it's got a slope of 2 because it goes up 4 and over 2. All right, we also know that the density of this plate is delta equal to 6 grams per centimeter squared. All right, so I'm going to run through a lot of stuff here for this problem before I actually get into the mass and the moments and the center of mass. So what I want is to look at a typical strip. Again, a typical strip is going to have some sort of x tilde, y tilde. It's going to have its own little center of mass. But let's look at the typical strip. Its length is going to go from the x-axis up to the equation y equals 2x. So its length is 2x, and its width is just going to be dx because we're going to make that width be ridiculously small. Combine those two things and we can get the area for our typical strip. The area, or dA, is equal to 2x times dx. The mass of our typical strip is delta, or 6 grams per centimeter squared, times the area. And again, the area is its own little function. So for each strip, its mass is 12x dx. Now, the last thing we need before we dive into all the moments in the center of mass for real is to look at the center of mass for our typical strip. So notice we're putting together all this information for our typical strip, and then we'll go ahead and do it over here with the whole plate. So the center of mass is going to be an x tilde and a y tilde, but here's the key. This strip is vertical, which means we're going along the x-axis. So my x-coordinate for any strip is just x, because we're going to drag them along the x-axis. The y-coordinate here, well, it should be halfway between 0 and 2x. So if you did it for y-coordinate, y tilde here would be 2x minus 0 and then divided by 2 to put it in the middle, all of which gets us x. So now that I have all the information for my typical strip, I can add them all together to get mass and moments and the center of mass. So the mass for my whole plate is the integral of dm, the integral of my mass function that I had over here for the typical strip. It's going to go from 0 to 2 because that's going to give me those rectangles all the way across the triangle. And my dm was 12x dx. We integrate that, which gives us 6x squared. Plug in 0, you get 0, so that's nice. But if you plug in 2, you get 4. 2 squared is 4, so we end up with the mass is 24 grams. Now, if we can find the moment about the y-axis, that will eventually then get us x bar, right? X bar, the center of mass for x, is the moment about the y-axis. Because remember, moment about the y-axis is how far away from it are you. That's an x-coordinate divided by the mass. So if we get that, we get x bar. Moment about the y-axis is the integral of the x tilde dm. Well, your typical center of mass for these strips for x is x, and then times our dm, 12x dx. So that gives us the integral from 0 to 2 of 12x squared dx. We integrate, get 4x cubed. And when we evaluate it, we get 32 grams times centimeters. All right, all of that then gets us x bar. X bar is just m sub y over m, so I take my 32 and divide it by 24, which gives me 4/3. And in this case, that's my x-coordinate for the center of mass, but I already know that for I have a relation between x and y, right? Basically, it's xx. So I get 4/3 and 4/3. And we could get that if we wanted by doing y bar, but to do that, we would need m sub x. And why bother when we could just use m sub y here, and that is fantastic. All right, I have one more example I want to do, and then we'll call it good. All right, our last example, I have a region here between the curves x squared and y equals x. I'm just here between 0 and 1 on the x-axis. So you can see I drew a typical rectangle in here. Oh, and its density is variable now. Its density is variable as a function of x, so its density is 12x for any point xy. So that's fun. It's getting more dense as you go across this thing. So what does a typical strip look like? Well, its center of mass is going to start with an x value. I'm using vertical strips because that sets up really nicely with my two curves. The y value for that, though, well, what I did is I added the two functions together and divided by 2. Basically, I averaged the two functions because I want that spot right in between the two. So I wrote it as x squared plus x over 2. The length of a typical strip is x minus x squared. Its width is dx, so its area function is x minus x squared dx, which means that its mass function, dm, is my density times the area, so 12x times that x minus x squared dx, or 12x squared minus 12x cubed dx. All right, so now that I have all this fun information for a typical strip, you really want to start here. Okay, start with your typical strip. Figure out where its center is, where its length, its width, then put together its area and its mass. Now I'm going to come over here, and you can see on this one, I had to find m sub y, the moment about the x-axis, and the mass. I needed all three things just to get to the center of mass. So the moment about the y-axis is that typical x times dm. Well, the typical x was just x. Oh, and I factored out this 12. So my dm had a 12 in it, and I just pulled that out front. So I have x times x squared minus x dx. I multiply that out, so I have the integral from 0 to 1 of x cubed minus x to the 4th dx. I integrated it, so I still have that 12 times 1/4 x to the 4th minus 1/5 x to the 5th. And if you plug in those numbers, you get 3/5. I then had to go back and do the same thing to find the moment about the x-axis. So for this one, y tilde was x squared plus x over 2. Much nastier example than that last one where they were both just x. So there's my typical y, x squared plus x over 2. Again, times the area function, or times dm, which was that must get way down there. Why did I write it backwards? I don't know. I did. So what I did is I did 12 and 2 cancel to give me a 6. I brought that out front. And if you multiply it out, you get x cubed minus x to the 5th. I integrated it, so I have 6 times 1/4 x to the 4th minus 1/6 x to the 6th, all evaluated from 0 to 1, and that gave me a half. But if that weren't enough, those are my two moments. I have the moment about the x-axis and the moment about the y-axis. I still need the mass. So the mass is just the integral of dm, which at least is a little bit nicer. So I brought that 12 out front. I cleaned up dm a little bit, x squared minus x cubed. Integrate, we get 12 times 1/3 x cubed minus 1/4 x to the 4th. Again, evaluated from 0 to 1. And that just gave me 1. So the nice thing is that since the center of mass for x is m sub y over m sub y was 3/5, divide that by 1, you still have 3/5. And for y bar, it's m sub x over m. Again, dividing by 1 leaves us with a half. So finally, our center of mass is at 3/5 and 1/2. So I hope you've enjoyed moments and centers of mass. It's been fun. Good luck.